Instructional design operates on a paradox. The support systems required to teach a beginner can cause a system to jam if applied to an expert. For novice skill acquisition, the standard is the worked example, a step-by-step demonstration showing exactly how to solve a problem. This chart plots instructional guidance versus learner expertise. The worked examples line starts high for beginners, dropping as expertise grows. Past a specific knowledge threshold, it crosses a line and actively degrades learning. This is the expertise reversal effect. Treating an advanced learner like a beginner is inefficient because instructional effectiveness is tied directly to the learner's existing knowledge structures. In 2001, researchers Cooper, Tyndall-Ford, Chandler, and Sweller designed a study to test an alternative to standard study methods for highly knowledgeable learners. 2 advanced learners were tasked with mastering a known spreadsheet procedure. Learner A reread the step-by-step example. Learner B looked away to mentally reproduce the steps. The data showed mental reproduction yielded significantly higher test performance. Researchers defined this as the imagination effect. It is the mental reproduction of a procedure or concept used to replace external study. Instructing a student to alter their internal mental process can outperform providing them with more external material to study. To understand why this happens, we must look at the cognitive architecture. Mental practice requires specific structural conditions in the brain to function. Human processing relies on 2 chambers. Information enters highly constrained working memory before passing into limitless long-term memory. Under the narrow limits of change principle, working memory can only process a few interacting elements simultaneously. If capacity is exceeded, processing stops. Novices lack data structures in long-term memory, so every step of a new procedure must be processed as a raw individual element. If a novice attempts the imagination effect on complex tasks, this sheer number of elements floods the system and causes cognitive overload. Novices require the external scaffolding of worked examples to safely guide these individual elements into long-term memory without crashing the system. For a novice, the volume of raw data simply exceeds the narrow capacity of their working memory, making imagination instructions ineffective. Experience changes how this hardware handles data. Experts develop schemas. Inside long-term memory, scattered interacting elements are bundled into a single cohesive unit. The environmental organizing and linking principle allows this massive compiled schema to be pulled into working memory as if it were only a single element. When experts are forced to study redundant worked examples for schemas they already possess, they encounter extraneous load. Redundant blocks flood the working memory funnel, crowding out the unified schema and causing a system jam. The imagination process avoids this. By mentally reproducing the steps, the learner directs limited working memory resources strictly to the intrinsic load. This strengthens the schema through repetition. For an expert, studying external material is often redundant noise. Imagination is a way to optimize their existing mental code. The imagination effect requires specific environmental parameters to function. The first condition is high element interactivity. Imagining simple, low-complexity tasks yields no learning benefits. The task must have a high intrinsic cognitive load. In 2006, researchers Tyndall-Ford and Sweller identified how presentation formats dictate the success of the technique. They highlighted the problem with split attention formats, where explanatory text is separated from a complex diagram. The act of scanning back and forth consumes the working memory resources needed to execute the imagination process. Integrated audiovisual instruction solves this. By routing text through the auditory channel and diagrams through the visual channel, the system avoids the visual bottleneck. A 2009 study by Leutner and colleagues established another boundary. Simultaneous physical activities can disrupt the process. If a student attempts to draw pictures while imagining a procedure, they are externalizing information. This splits attention and can overwhelm the system. To successfully implement internal practice, the designer must ensure external load is minimized, so the internal processor can run at capacity. A closely related cognitive phenomenon utilizes the same architectural rules, the self-explanation effect. Self-explanation is a mental dialogue, relating a new procedure back to foundational domain principles. Self-explanation is essentially the act of imagining a process while simultaneously justifying its steps against prior knowledge. In 1989, researcher Micheline Shi demonstrated that principle-based explanations generate new inference rules. This links appropriate actions with specific conditions to build procedural skills. This highlights a structural limitation. Just like imagination, self-explanation fails in novices because they lack the long-term memory structures required to form these links. Both phenomena suggest that advanced learning occurs through internal mental rehearsal rather than the passive consumption of external content. Imagining and self-explaining are forms of deliberate practice designed to automate cognitive schemas. This suggests a primary design principle. We should not assume a concept is fully mastered just because it is initially understood. Second, instructional material should scale back guidance based on the learner's accumulation of expertise. Finally, at high levels of expertise, designers can move away from worked examples and encourage learners to mentally reproduce and explain the system. This chart maps the progression from novice to expert. We start beginners in the study phase, move to the self-explain phase, and conclude with the imagine phase. Effective instruction is about facilitating the correct internal mental state at the moment the learner's cognitive architecture can support it. Internal processing is what ultimately drives expertise.